Hello everyone, thanks for watching this video. My name is Guangshu Yang. I will be presenting communication lower bounds of collision problems via density increment arguments. This is joint work with my advisor Jiapeng Zhang. We are both from USC. I want to start by introducing the definition of collision problems. For the query model, there is an input Z. The goal is to output a collision that is a pair of distinct indexes I and J such that Zi equal to Cj. This problem has been studied in quantum query complexity and cryptography before. However, in communication model, is little known about this problem. For communication model, there is a natural extension for each Zi, Anis holds the first half bits of each Zi, and Bob holds the second half bits of each Zi. That is, the Anis holds X and Bob holds Y. They want to find the distinct indexes I and J such that xi equal to xj and y equal to yj. There are some motivations for collision problems. The first motivation is from cryptography. Previous work called collision problems multi-state double intersection problem. And they show that the communication lower bounds for this problem implies the collision resistance of compilers for black-doored random oracles. The second motivation is from proof complexity. They call this problem collision problems beta pigeonhole principal problems, BPHP. And they show that the communication lower bounds for collision problems imply some proof system requires exponential size to refuse BPHP. If we consider the uniform input distribution for collision problems, there is a simple protocol for Anis and Bob based on Bossy paradox argument. That is, Anis randomly choose n to the 1/4 power coordinates with same value and send it to Bob. Bob can find the condition with high probability by Bossy paradox argument. In detail, let S be the set of coordinates that Anis send. We know that for any ij in S, xi equal to ij. Moreover, since the Bob's inputs are uniform distribution, so if the size of S is n to the 1/4 power, then by Bossy paradox argument, there is I and j in S such that yi equal to yj with constant probability. Previous works conjectured that this simple protocol is optimal, but they only proved a weaker lower bound. They use a technique called query to communication theory, lifting series. In detail, they first prove communication lower bounds for lifted function via degree to rank lifting. Then they build on the lower bound for the lifted function. They prove a lower bound for collision problems via reductions. Since there is a loss in the reduction, their framework can't prove the tight lower bound for the collision problems. For our contribution, we prove the tight lower bounds for the condition problems, which implies the simple protocol based on both paradoxes almost optimal. For technical contribution, our paper, our first paper, which used the density resource partition for the non-limited functions. The density resource partition is a common technique in the query to communication limiting series, but the previous papers only used it to prove communication lower bounds for limited functions. Moreover, our technique can bypass the barrier by using information complexity and query to communication limiting series. Based on previous connection, our results also have some applications in cryptography and proof complexity. We have some applications in collision resistance in cryptography and prove some potential lower bound for some proof systems in proof complexity. Next, let's focus on the proof. In the communication complexity, a communication protocol can be described as a binary tree, where each node describes Alice or Bob who speak, and the other one describes the communication bits in each communication round. Moreover, the protocol partitions the truth table of the problems into different rectangles. So each node in the protocol tree is corresponding to a rectangle, which is a subset of the truth table. Next, I present the main idea of the proof. Before give the formal proof, first we review the density resource partition in the query to communication limiting series. We call a distribution density distribution on J if for any subset of J, the mean entropy of the marginal distribution of the distribution on I is large, and for other quantities that's not in J is fixed. Here is the picture to describe the distribution. Some quantities are fixed, and for the other quantities with high block-wide mean entropy. There is a key number in the inquiry communication limiting series shows that a uniform distribution on any subset can be decomposed into multiple dense distributions, and the expected size of the fixed quantities is less than the decrease of the density function plus 1. Our proof is a decomposition algorithm, giving any protocol for the condition problems. Our decomposition algorithm has two processes in each communication round. The first one is the density resource partition. That is, we further decompose the rectangle of each node into dense rectangles. X is dense on some subset, and Y is also dense on some quantities. We use the density resource partition to keep the dense property. In detail, we prove the number 2 based on the density resource partition. That is, the expected size of fixed quantities in the left rectangles is almost the upper bound by the communication cost of the protocol. The second one is the labeling process. The labeling process labeled the inputs in each dense rectangle that Alice and Bob can find the collision. We use it to prove the upper bound of the success probability of Alice and Bob to find a collision. In fact, we prove the number 3 that by the labeling process. That is, if Alice or Bob can find a collision with the constant probability, then the expected size of fixed quantities in left rectangles is omega n to the 1/4 power. By combining number 2 and number 3, we will finish the proof. So next, we will go through the number 2 and number 3 one by one. First, we focus on number 2. This is the density partition when Alice speaks. At the beginning, this is the rectangle. If Alice speaks, it will partition x into x and x star. And for each x and y, find x and y in this rectangle, we do the density root partition on x, which further decompose x into x1 to x4. And we know that y is dense and xi is also dense. We also have this property that the fixed size, expected size of fixed quantities is upper bound by the density function. So for the proof of number 2, we use the density increment arguments. At the beginning, the density function is 0 at the beginning of protocol tree. And in each communication round, the density size decreased, so the density function increased at most 1. By the number 1, in the density resource partition, we have that the density decreased at least the expected size of fixed quantity minus 1. Since the density function is always non-negative, so we have that the total expected size of fixed quantities is upper bound by the 2 times the communication cost of this protocol. Next, we focus on number 3. This is the labeling process when Alice speaks. So first, we start with the density. After the density resource partition, we start with x1, x2, x4, and y. So we do the labeling. Labeling means that we label some inputs that for Bob, label some inputs, which first we choose some y, such that in Bob's view, they can find the collision in the fixed part of Alice. So we label the inputs in this rectangle. And based on this labeling process, we can prove the number 3. Here is the proof outline. First, we use a claim that if Alice or Bob can find the collision with constant probability, the total probability of the labeled input should be omega 1. This is the direct calculations. Then, in each labeling process, since we keep the dense property of the rectangle and by both paradox, we can show that the probability of labeled input increased upper bound by the fixed size of expected size of fixed quantities. And take the summation for the all labeling process, we can prove the lower bound of expected size of fixed quantities, which will give the deserved result. Finally, I give a summary and proof outline. In this paper, we prove the communication neural bond of the cognition problem is omega 1 to the 1 over 4 power. The proof outline is follow. We use a decomposition algorithm. In each communication round, we do the density restore partition for the rectangle to decompose each rectangle into multiple dense rectangles. Then we do the leveling process for each dense rectangle. By the lemma 2, we show that the expected set of fixed coordinate in the left rectangle is upper bound by the communication complexity, which proved by a density increment argument. By the lemma 3, we have the expected set of fixed coordinate in the left rectangle is at least omega 1 to n to the 1 over 4 powers. This is proved by both the paradox argument. So the major open problem for the cognition problem is that can we prove the communication neural bond in the numbers unfolded model? This result will have important applications in proof complexity. That's all. Thanks for your listening.